So hello, welcome to online version of this course, I guess. No day, sure. Um, for those of you watching this video on like YouTube and whatever, ignore everything I'm about to say. But those of you watching it live, part of the reason to do it live is so you can ask questions like normal. I'm not necessarily gonna have everything visible for like hand raising and stuff. If at any point during this lecture you have any questions, please just unmute yourself and interrupt me, same as I asked for with lecture. Um, I can't, I might not notice a hand otherwise because I have my screens filled with various what would be demos in class, but instead will be extra videos I'm showing. So interrupt me as needed. I just want to state again that lab this week, there was no lab today since we can't do anything on campus today, and it seemed not right to do lab to cancel lab Monday and still make the Tuesday people do lab. Just didn't seem equitable. So labs on Tuesday will be canceled. I will be on campus anyways, even though I don't have any classes if I cancel lab, but I can do office hours and help. So if you want to see me, come by. We're just gonna skip lab one, go straight to lab two. Lab one kind of sucks anyways. Um, as I said, interrupt me as needed. If you're watching this live, I will gladly hear someone else talk and not just it's really weird to lecture just at my computer as if no one else is around. So, I'm gonna get started though. So we're gonna start today chapter two, motion in one dimension, which is the beginning of actual physics. Everything we did so far was basically just pure math. And yeah, we're gonna talk about motion. Now, if we're going to talk motion, we have to first talk about if we're going to have things moving, about position. And so let's start there. Um, yeah, if you want to define the position of anything, you need two bits. No one would find a position we're gonna like measure something, right? And be like, okay, this thing is so far away. But you need that end. You need where the zero is. That whenever you define the position, we have no, it's what's called an absolute reference frame. That in the on Earth, there is no absolute reference frame, no set point we measure from. And so whenever you're measuring the position, you have to have your 0 point, where you measured from, where you put the end of your tape measure to start at. Um, and you always have to have that zero. Also, to measure something, you have to have a direction. If I just say something is so many, centimeters away from a point, that's going to give me a circle of possibility of where it could be. That when we define the position, it's also going to need a direction. That I can say that, oh, you can't see much behind me. My comics are about a meter behind me. If I say the comics are a meter away, they could be in any direction, which in my room you can't see it is actually debatably true. But saying it's a meter behind me gives it a location. Now, in physics, every term we introduce is going to get a symbol to represent it. And position is kind of annoying because it gets three. Position will always be labeled as X, Y, or Z. And it's that because it depends on which axis it is. X for the horizontal, Y for the vertical, and Z for into and out of the page. We're not going to do much three-dimensional in this course, so for the most part, we can ignore Z, but we will just talk about X and Y. I did that backwards. X is horizontal and Y is vertical. It's really weird lecturing online to me. I hate it. So, um, now units, we're going to use meters. And yeah, anytime you see an X or Y, that just means position. For the most part today, we're only really going to talk about X. We're going to do most of Y Wednesday. Now, if we're talking about motion, though, the position doesn't really matter. Motion is things moving. So we got to get into, how things move. And that gets into displacement. Displacement is defined as the change in position. So you're going to see this delta symbol a lot, the triangle. It's a Greek capital delta. Delta means change in. And so when we talk about displacement, displacement is just your final position minus your initial position. I did it in X's. The same could be true with Y also. And it's just a way of talking about where something was and where it is. but it's not a path taken. It is just your final minus initial. Now, the reason I'm stressing this is because if something starts moving, you like to think, oh, it should be how it moved. But we're not doing that here. To stress what I mean, let's say I have this random spaceship at position x1, and it goes to position x2. Its displacement is just the minus x2 minus x1. And when it did this straight path across, my displacement is just that thing. But let's say it goes from x1 to x2 like this. That's the same displacement. You see, when we do displacement, we are just saying final and initial. We are ignoring the path taken. And so for displacement, this is the same as this. Because in both cases, it started at x1, it ended at x2. This is weird because it means you can have zero displacement and have moved. That if the ship starts back at x1 and does this, that's zero displacement, even though it moved, because it started and stopped at the same spot. See, the idea this gets into is that displacement and distance are not the same. If I was to drive into to Delhi right now, which, roads are fine, probably could, but I'm not going to. I Google mapped it from my house to this college, right? And according to Google Maps, it is 21.8 miles that my car drives. But Google Maps has a measurement tool in it, not often used, not well known. But according to the measurement tool, that if I just do a line from my house to Zuni Delhi, it's 14.5 miles along the straight line, as the crow flies, as they say. You see, when doing this blue path, the driving line, that's the distance I would take. But the displacement is just the 14.5 miles. It ignores going into a circle, going around a bend, going uphill, going downhill, going up and down a few more times. It's just the final initial ignoring the middle. Likewise, if I throw something straight up and catch it at the exact same spot, the distance it traveled is twice the height because it goes that high up, that high down. But its displacement is zero because it started and stopped in the same spot. So even though it moved, well, that time it went way out, but even though it moved, it still has zero displacement. Now, this makes it seem like displacement should be pointless, right? Like it's saying, this way, I can't catch. Nothing happened. Obviously, something did happen. And displacement is saying nothing happened there. So you would say, like, why the hell would we need that when distance would say, hey, it did this thing? But it ends up mathematically, and therefore physics-wise, displacement can give us more information. And the reason why is because of the idea of what is called a vector. You see, all quantities in physics, and really in anything mathematical, come in two flavors, vectors and scalars. In that, what it is a vector is something that has both magnitude and direction. You see, vectors say how big it is, but also which way it's going. And so the vector will include more information. That's going this way is not the same as going that way. Displacement, I'll put this up now, and position are both vectors. That direction must be included. And now we're doing one-dimensional motion in this chapter, right? Like that was the opening slide, motion in one dimension. When we do two dimensions, this gets more complicated. We'll save that for next week. That's next week's problem. But for now, if we're doing one dimensional, things will either go in the positive direction or the negative direction. And we'll just define everything as positive or negative. Now, the standard, I didn't write this here, so I'm going to just draw it out, is that we'll say anything to the right is the positive x. Anything to the left, that is a horrible left, is the negative x. Likewise, anything up will be positive y. And anything down will be negative y. That is the standard. It doesn't need to be that, but it's the way it's normally done. And so we'll have to say, and the whole reason that displacement becomes important now is when I throw this up and down, I'll say it has some positive and then some negative. And that's why it had zero displacement. It's because the positive and negative cancel each other out. Okay. As I said, any questions, interrupt me at any point because I
As I
can't. Yes.
Sorry, so you said that positive and negative cancel each other out, but
In this
isn't
case,
it in this case, it's not like it becomes a negative automatically, just cancels each other out.
no, because so when I throw this, right? Hold on, let me grab. Nope, I don't have that video open because I didn't think I need it today. So when I throw this up and catch it, right? It traveled up some distance and then it fell that same distance. Well, if I do displacement, if I look at just the half, then on its way up, it had positive displacement because it went up. And on the way down, it had negative displacement because it went down. But if it goes the same height up and the same height down, which it will do unless I like move where my hand is, that will be zero displacement because it would be like plus a half meter, minus a half meter, canceling to zero. Then in this case, it cancels to zero, assuming I catch it at the same height. Now, if I start at one height and end at a different height, which I'm about to do in a second, then you're not going to have a net displacement, positive or negative, depending. That make more sense?
Yes, thank you very much.
No problem. So let's do when it's not zero. And I'm going to grab, oops, I'm on drawing still. Clear, um, click, dink. Okay. This picture stolen from a textbook, but I'm going to do it kind of live too. Let's say I have a cult starting at some spot, and I'm going to measure my 0 point from this the black thing that's going up right. I don't know if you can see my mouse or not, but if you can't, there's on the track, there's a black thing in the middle. If I have the cult do this, we can talk about the displacement on that path. And I'm gonna make it go slow. So when I talk about it. And you know what? We're also gonna mute it. And just for fun. Nope. Okay. So when I do this, we can talk about the different parts of its movement. If I was to plot its position as a function of time, I would get this orange graph right here. The one to the left of the video. Because what's happening is that the first bit on its way up, it has a positive displacement as it goes up. But then when I continue going, it's going to come down and then past my initial point and then past my zero. This will have a net negative displacement. And it's a net negative displacement because it goes from heel to heel. And it doesn't matter that it went up and down in the middle. That I'm just saying it went from this spot to this spot. And that's all that displacement cares about. And so even if it did do that, all those stuff in the middle. And so this would be a net, I mean, I'm kind of tilting my coordinate system, but would be a net negative displacement because in the end, it went to the left. Even though it started going to the right, it started going positive, then came back down. And it's because a little bit of this, the going from there to there kind of cancel each other out before it comes down. Put that over to the side again. Now, I already said to measure position, you have to have a 0 point. As I said, I made the 0 point, the little thing sticking up. In this picture, it's the speed limit sign. You always have to have a 0 point. Wow. This next problem, I really should have thought about for doing online, but it doesn't work. Oh, well, I'm doing it anyways. Normally I do this one live in front of the room and I didn't think about it. But you've noticed by now when I am teaching in person, I pace a lot. I kind of go back and forth across the room a lot. Um, so let's do that. Let's say we have me pacing back and forth. Sorry, I'm seeing who I could grab to pace. Say I'm the eagle will work. Let's say I got something pacing back and forth in the room, right? And let's say I start in the room and I want to go your directions. And I move 7 meters one way then 12 meters the other way, and then back the other way is 9 meters. The question is, what would be the net displacement? See, I can say the distance traveled would be 7 plus 12 plus 9. But if I want to do displacement, it's just final minus initial. And the thing is, assuming I have my axes and define my 0 point, well, I'm going to define my 0 point as wherever the hell I started because I want to measure from where I started. So let's just make that my 0. If I do that, my xi will be 0. So final minus initial would just be final. Assuming I define my direction, I'm going to make to the right positive as is standard. I can go and work this out because everything is a vector. That anything to the right will be positive. Anything to the left will be negative. So I have a positive 7, but then I'm going to move a negative 12, and it's negative because it's to the left. Although I'm doing my left, not yours. So to the left. I then move to the right again, 9. Because I move to the right again, 9, that's then in the positive again. And so my net displacement wouldn't be 7 plus 12 plus 9. That would be the distance. It'll be 7 minus 12 plus 9. Because of the idea that anything to the left is negative, which is 4 meters. This is a net displacement of 4 meters. And so once again, it seems like it's giving less information, but it's giving more because it's accounting that me walking this way and that way all at the same. Now, that's all well and good. I drop stuff to say, oh, look, things are moving. But it gets into also like, well, how fast are they moving? And so let's get into speed. When you are in your car and you're driving, your speedometer gives you what is called your instantaneous speed, the speed at that moment. We're not doing that yet. For now, let's talk about the average speed. That if someone is driving, how fast do they go on average? Average speed is defined as distance divided by time. Um, I don't really use distance often. In fact, I'm probably never going to use distance again. But in general, I use the symbol D for distance. So really, I can say speed is D over T. Speed is a scalar. It doesn't care. Means it's always positive. That means going this way and going that way are exactly the same. And it's of note that this is the average over a trip. So if I'm driving from Oneonta to Delhi, let's keep using that example. My average speed is not what my speedometer says. It would be me taking that map I had earlier with the 21.8 miles was the distance. Sorry, I'll come back to that in a second. But this, right, that blue path was 21.8 miles. And just dividing that by the time I took. It doesn't account for, oh, here I'm doing, 60. Here I slow down to 30 because that speed limit area. Here I speed back up. It's just total distance over total time. Now, what that means is the average speed ignores any variations in the trip. It ignores when you go fast, when you go slow. It's just total time, total distance. Now, units is distance divided by time. And so dimensional analysis wise, distance over time, that will be meters per second. Now that I've gone in depth about speed, fun fact, we're never going to use speed. Speed is kind of useless because speed is a vector. And it says going this way and going that way are the same thing. Now, we also average speed. No one gives a shit about average speed, really. You want instantaneous. But see, because the fact this is a vector, because the fact it's a scalar, I misspoke. Because the fact it's a scalar, this is not going to be that useful to us. And so in physics, we won't use speed. Instead, we will use something called velocity. See, while speed is distance over time, velocity, or at least average velocity, that little AVE there stands for average, is displacement over time. That it's just going to be how much, not the distance you traveled, but just your displacement. Symbol for velocity is a V. So anytime you see a lowercase v, that's velocity. Traditionally, you're going to start our stopwatch at the beginning thing. So almost always T initial is 0. But what this does is it says that when something is moving, we can just say it's Yeah, displacement over time. Now, going back to that little cult video I had, that this guy going up, the distance it traveled, this metal thing, you can't tell here, but just have to trust me, that this metal rail is a meter long. So when it goes like this, its distance was about a meter and a half, but its displacement was about negative half a meter. Negative because it has direction. The time that happened is the same either way. And so this means the average speed and average velocity won't necessarily be the same. Now, direction will be important, but time has no direction. Time is a scalar. You don't go like 30 seconds that way, it's just 30 seconds. And so, whatever your direction of displacement is, that will be the direction of your velocity. If you have positive displacement, positive velocity, negative displacement, negative velocity. Um, Also, sometimes I'll ask for the magnitude of velocity. This will come to any vector. And as the semester goes, we're going to introduce more and more and more vectors. If I ever ask for the magnitude of a velocity, just give me the value, ignore any sign. So, like if the average velocity is negative 5 meters per second, the magnitude of that would just be 5 meters per second. I'm ignoring the direction. And units are still meters per second. Now, this once again goes into a weird thing because it's saying things going, you know, I said before when I throw this and catch it at the same height that its displacement is zero. That means its average velocity was zero. And that seems kind of weird because it's saying on average it's not moving. But that's actually true because on the way up it has positive velocity. On the way down it has negative velocity. So yeah, on average it's not moving because these directions. Oops. Another way to talk about this, let's say I got two calls, a blue one and a orangish one. And they both go from point P to point Q in the exact same amount of time. Both of these calls will have the exact same average velocity because they have the same displacement, same time. But they will not have the same average speed. The blue call traveled faster, speed-wise, because of the fact it moved further. It went up and down. You see, the reason this cancels out is because when the over here, the velocity is going to have some positive component. And down here, I have some negative component, and then more negative component, and then some positive component. And these vectors start canceling each other out. Now, this is all still, I'm not going to lie, kind of in the realm of it doesn't really matter though, because we're still talking about on average how fast something is going. That if you're driving down the road, you don't care what your velocity or speed is on average. You want to know how fast you're going at the exact moment you pass the cop who's sitting there. And we can get from our averages to that instantaneous if we start, well, let's do some graph stuff. If you graph position versus time, nope. If you graph position versus time, the slope of your graph, that is velocity. And so if you take this and have a position in x, time in t, if it's a nice straight line, means it's a constant velocity, the slope throughout it, that is your velocity. Because if, right, how to find a slope, right? It's change in y over change in x. Well, here it's change in position over change in time. It's the same equation. And so if you graph position versus time and get that slope, those who had calculus, derivatives shit happens here. Um, we can say that that average velocity, once again, is just change in position over change in time. Damn it, do what I'm trying to do. There we go. So if I want to find my velocity average between B and A, it would be my position at B minus my position at A. My time at B minus my time at A, which in this case would be 0 minus negative 20 over 10 minus 0. or my velocity between B and C. My position at B is 40, position at C is 0, time at C is 30, time at B is 10. So we get the same thing. That's interesting. Sorry, my computer just put up a weird alert. Should be fine. We'll find out. Now, if your velocity is not constant, so this graph, once again, that was this guy. Oops. Nope, that's a lie. Yeah, it was. That graph was this guy again, right? His velocity is not constant because initially it has a positive velocity on the way up, and then it gets a negative velocity on the way down, that the velocity is changing. And so what that means is that if I graph position over time, I won't have a nice straight line. Because if the slope is velocity and velocity is changing, the slope will be changing. But I can find the average velocity between any 2 points. Because if I want to find the average velocity between any 2 points, I'll just find the slope between those 2 points. That if I say the average velocity between A and B, which is position of B minus position of A, time B, time A. The average velocity between D and A will be position D, position A, time D, time A, and so on. And this gets us closer to something that's, actually useful because we're saying, okay, we can get the average velocity over any range of this just by looking at 2 points. And I mean, when I go from A to B to A to D to A to E, I'm getting to bigger areas. Therefore, honestly, kind of less useful information. But what if I went the other way? What if I shrunk the time period? What if I, instead of looking at A and B, I looked at between A and like right here? Or maybe I shifted B and looked between um that red line and like this yellow line, or got even maybe even closer. That if I start making my lines closer and closer together, the average over a smaller area becomes a lot less average. And this is how we will get out instantaneous velocities. You see, our instantaneous velocity is the limit when time goes to zero. Those of you with calculus, I'm taking a derivative. But if I make that time pretty small, basically I'm taking the average over a moment. And if I take that average over a moment, that's what you're doing at that moment. And this is your instantaneous velocity. That your instantaneous velocity is how fast you're going at a spot. How fast were you going when you pass that cop running radar? And all it is by taking that average over a fraction of a micron of a tiny bit of a second. Now, if I make my time period impossibly small, that means my distance by definition should be impossibly small. And so any variance I can have between distance and displacement kind of go away. Because if I'm looking between here and here, I don't have time for in the middle of one of them for it to go some wild, crazy path. And so what happens is when you hit instantaneous, is that the magnitude of instantaneous velocity is instantaneous speed. That speed and velocity become almost interchangeable again. The difference is, though, is that speed is a scalar, while velocity is a vector. And so when I make this super tiny, I can say my speed, I can say my velocity, the instantaneous, not average. Honestly, we're never going to deal with averages at all. Despite the fact I've covered over half of today on this, we're not going to deal with average at all. Because basically the same, it's just one has a direction. And at this point, you can see that velocity is much more useful because speed is just saying, hey, we're going 80 miles per hour. Velocity is saying, which way are you going 80 miles per hour on that highway? Because, it makes a difference which direction you're traveling that 80 miles per hour. You want to go one place and you're going the opposite direction, might not be helpful, especially when now I'm picturing you going like the wrong way in the lane. And so it becomes much more useful because this direction is included. Now, when your velocity is changing, like in the video I keep showing of the car going up and down the ramp, normally that would be done in person, but hey, I'm not at school. That also, we can talk about when the velocity changes also. That is acceleration. Anytime your velocity is changing, you have acceleration. The symbol for acceleration is a lowercase a. And acceleration is, by definition, change in velocity over change in time. Final velocity minus initial velocity over final time minus initial time. Units, the unit for velocity is meters per second. So acceleration is meters per second divided by second. That is meters per second squared. It is also a vector. What direction your acceleration is makes a big difference. Now, if you're traveling at a nice constant velocity, a quick thing on this videos I keep using, this blue thing on top of the cult is an accelerometer. It's a visual accelerometer. The lights on it represent acceleration. So the more lights, the more acceleration, and it will tell you which direction. If I just move this at a constant velocity, ignoring when I push on it, it basically had no lights until it hit the end. It had a little bit because there's some friction there, but that's because it's moving at a constant velocity. That if your velocity is constant, your acceleration is zero. That acceleration means change in velocity. And now people like to think positive acceleration go faster, negative acceleration goes slower. And it would be nice if that was true. But it ends up it's more complicated like that. That a positive acceleration could mean faster or slower, and a negative acceleration could mean faster or slower also, because it's just showing which way it is pushing. See, if I go back to this same video that I've been using over and over and over again, once again, the lights are the acceleration. On the way up, I have red lights, meaning acceleration to the left. On the way down, I have red lights, meaning the accelerations to the left. What we get in this case is that, really, I should just crop this video, is that on the way up, there's negative acceleration and it's slowing down. On the way down, there's negative acceleration and it's speeding up. If your acceleration velocity point in the same direction of each other, you're going to go faster. If your velocity acceleration, your accelerations, sorry, if your velocity is positive and your acceleration is positive, you're going to go faster in the positive. If your acceleration is negative and your velocity is negative, like this, you're going to go faster in the negative. But when they're in different directions, if your velocity is positive and your acceleration is negative, or vice versa, I don't have vice versa shown here. If your velocity is negative and your acceleration is positive, that is when you slow down. So when they're in the same direction, you go faster. When they're in opposite directions, you go slower. Okay. Now, I'm about to completely change my notation. Some physics you'll see the x initial, x final, but standard most of the time, it isn't what's used. Mostly what is used is what is called the sub-knot notation. We did the math packet. I talked about sub-knot a little bit. It's just something a subscripted zero. And here's the general idea. If I'm going to time something, I probably want zero to be when it starts, right? You very seldom start a stopwatch and be like 3 seconds in, go. Sometimes with races and stuff, but most of the time you start the stopwatch at the beginning. Almost always, initial time is zero. And when I say almost always, I am never going to give you something that this isn't true. You'd be a really weird situation for initial time to not be zero. And so what we're going to say is when we're doing something, we're going to go from when time equals zero to some other time. So instead of time initial and time final, we can say zero and just t. Because if we only have one time, why put a subscript? What we'll do with that is we'll say anything else when time equals zero, instead of subscripting with an initial, we'll subscript it with a 0. And so when your velocity when time equals 0 is v sub naught. Your position when time equals 0 is x sub naught. Well, once again, sub naught just means subscripted zeros. And your time when time equals 0 is 0. That's what I'm getting at here. And what we'll do is instead of saying initial and final, we will have when time equals 0, your initial will be initial position will be x sub naught, your initial velocity will be v sub naught, and your final will just be x and v, no subscript. And so I'm not going to use I and F for the rest of this chapter, or really the next few. It'll just be subs naught and regular to be your initial and final. And with that in mind, we can define the 3 equations that are going to be how you solve every problem this chapter and next chapter. Obviously, there's going to be some nuances as I go forward because it's a chapter and a half still to do. Well, chapter and 3/4. But this introduces us to what is called kinematics. Kinematics is a special setup where we're going to say, hey, what if acceleration is constant? You see, if your acceleration is constant, I mean, that's going to be true a lot of the time. This video I kept doing, the acceleration was constant at any point that wasn't me touching it or hitting the, or that's touching it again. That when I let go, that acceleration is constant from here all the way back down. And if we do this, let's say acceleration is constant. Well, if acceleration is constant, that means instantaneous acceleration is average acceleration. Because if it's not changing, it just is what it is. It is. Side note, if acceleration is changing, change in acceleration divided by time is called a jerk. Like you jerk to a stop. We're never going to talk about that though. And if your acceleration is constant, what we're going to say is our initial condition will be our sub naught notation. Our final will be just no subscripts. And with that, we know acceleration is change in velocity over time. That means acceleration, and now instantaneous acceleration, because instantaneous acceleration will be our average acceleration, will be v minus v naught over t. I mean, if I wrote the t minus t naught, but once again, t naught is by definition 0. So, screw that noise. Now, this equation is not going to get used in this form very often. But if I multiply both sides by t and add v naught from both sides, I get this equation. There are some kind of 3, kind of 6 equations important to this chapter. Why it's like that, I'll get into on Wednesday. But this equation is one of the most important equations we're going to have. This is one of all the stuff we did today, this is the first one you're really going to need. That what this is velocity as a function of time. That you can always find velocity as a function of time by saying it's your initial velocity plus acceleration times time. Now, I'm going to bring this equation back in a second, but let's do some more math. We also said V average is x minus x naught over t. I said x final minus x initial, t final minus t initial, but same thing. If I do some math to this, I can do the exact same math to this I just did to velocity. And eventually I'll get that x equals x naught plus v average times time. Just the same math happens. I'm not going to show it again. I multiplied by t, I added x naught. Now this is a useless equation. Don't bother writing this down. Quick side note. I will often show the derivation of equations. I show the derivation of equations so you can see where they came from, that I'm not just pulling shit out of my ass. You never will need to derive equations yourself. So you will not need to know what I'm showing now. But I want you to see it isn't just coming from nowhere. You see, let's say I want to take an average, right? This is V average in here, which is pretty useless. But if you want to take an average, you add things up and divide by a number. And if we have an initial velocity and a final velocity, the average velocity of my initial and final will be initial plus final divided by 2. That's how you take averages. If I take that V average and shove it into the equation to its left, and don't forget from a few slides ago that V equals V naught plus AT, What I'm going to do is I'm going to take this V, oops, and I'm going to shove it in right there, giving me that x equals x naught plus v naught plus at plus v naught. Now, up here, I got a v naught plus v naught. V naught plus v naught is 2v naught. I'll factor through my 2 and my t, and I get this equation. This is the second important equation that you need to know. That this equation says that position as a function of time is initial position plus initial velocity times time plus 1/2 acceleration times time squared. So what this says is if you know time, you can get velocity. And if you know time, you can get position. Sometimes it's useful, though. You don't always have time. Sometimes you got everything but time. So maybe you have position and want velocity. But I have two equations with time in it. I'm going to do this next bit a little fast. You do not need to know the steps, and this is going to get ugly as hell. But if I take this left equation and solve it for time, and shove this into my right equation, into both t's, you get this bullshit. If I factor through that squared, cancel out an a, multiply everything by a, cancel out those two terms, negative 2 v naught squared plus v naught squared is negative 1 v naught squared, and rearrange it, I get my third equation. And that is your third kinematic equation. These are the kinematic equations. These are the ones you need. And what these equations say is this is how we're going to solve these problems. That these three equations will be solving everything we need to know. This is the most important stuff we're covering today. That in this equation, a is acceleration, t is time, v is final velocity, v naught is initial velocity, x is final position, x naught is initial position. Now, when we're dealing horizontal, which is all we're doing today, we're going to basically always make x naught 0. Because if we have something moving in x, we're just going to have it start at the 0 point. Ignoring x naught, which side note, I'm going to say this right now for Wednesday. This will not be true in y. Y naught is going, this is not, things are going to change when we go up and down. But in horizontal, assuming we not count x naught, if you know any three terms, you can get the rest. And that's what we're going to be doing with this, is that we'll use these equations to rearrange and solve for whatever it is we need to solve for. What do I got? 7 minutes? Okay. I'm going to do an example. So any questions? No one's unmuting, so I assume there's no questions. As I said, these equations, very important. All right, let's do a problem. And we are going to go Fast and the Furious. The first one. So, the first Fast and the Furious has a scene where Brian is traveling at 130 miles per hour, which is 58.1 meters per second. I did the unit conversion for you. And he hits the nitrous oxide. When he hits the nitrous oxide, he goes up to 150 miles per hour, which for the record is 67 meters per second. He accelerates for 3 seconds. What's his acceleration? How far does he travel? Okay. Now, last week we went through how to solve problems, so I'm going to use that same logic. Step 1, I'm going to draw a picture. Boom, there's my picture. And then I'm going to label my knowns and unknowns. So what I'm saying is he's initially driving at 58.1 meters per second. That's V naught. When he hits the nitrous oxide, he accelerates to 67 meters per second. That's V. He accelerates for 3 seconds. That's T. Now, this one's not written, but I want to know how far he traveled. So I want to know how far he traveled from his initial. Because I want to know how far he traveled from his initial, I'm going to make my x naught 0, because that's what I'm going to measure from. And also, I always make x not 0, as I said before. And I said, what's his acceleration? So A. How far does he travel? What is x? Now, I should check if everything's SI. It is, though. I did the unit conversions for you. And now becomes the equation part. And how you're going to do these kinematic equation problems is once you have this written down, you're going to drop down your kinematic equations. Those three equations, these equations are how you do it. And what you're going to do is you're going to try to match what you need. Now, I am solving for time first. No, I misspoke. I am solving for acceleration first. I know time. I'm solving for acceleration first because that was what part A was. And so all three equations have acceleration, so I can use any of them. However, I don't know x. And this equation has an x right here. This equation has an x right there. I can't use these equations because they have those x's in them. And I don't know what x is. And so I have to use the top equation. That's the only one without x in it. This is the secret to these physics problems. Write down your knowns and you're going to be, for chapters 2 and 3, you're going to be using these equations. You just write down your knowns and figure out which one has the terms you know / want. I know V, I know V naught, I know T, I want A. And so I'll take that equation and I'll solve for acceleration. I can subtract V naught from both sides. I can divide both sides by T. And what I'll do is I'll plug in my numbers. That V was 67, V naught was 58.1, T was 3, and I get 2.97 meters per second squared. Now, that was only half the problem. What do we got? 3 minutes. Cool. But now that I know that, I can try to do part B. It's weird. Normally, I pause for as long as everyone in the room is writing, but since I can't see anyone, I have no idea how long that is. I'm just going to move on, and if anyone needs me to go back, yell at me. I hate teaching like this. It sucks. Anyways, so let's find the position. Now I'm solving for x. Now that I'm solving for x, I can't use the top equation. The top equation doesn't have x in it, so that's useless. But in the second equation, I know x naught, I know v naught, I know t, I know a, I know t. In the third equation, I know v, I know v naught, I know a, I know x naught. I could use either of those equations. I could use the second equation or the third. Either one works. And this will often happen. There's not always exactly which one you need. Sometimes you can use multiple equations. What I said last time and I stick to, always use the simplest one. The more complicated you make it, the harder it will be. I am solving for x. So I'm going to do the equation that starts with x equals. I'm going to use the second equation because if I don't have to rearrange it, I can't make a mistake rearranging it. And so I'll just take that equation and I'll just plug in my numbers. X naught is 0, V naught is 58.1, T is 3, 1/2 A, T squared. 58 times 3 is 174. 1/2, 2.97 times 3 squared is 13.35. And that's the distance. Now, if you decided to use the third equation, if you said, no, I want to use V squared equals V naught squared plus 2AX, you could have and rearranged it. You would have gotten the same answer. It would have worked. But as I said, why bother? You're just making yourself have more effort. That's exactly 250, and that's exactly where I wanted to end. Yay. So we're going to stop there. Once again, there is no lab today for obvious reasons, no lab tomorrow for less obvious reasons, but the same thing. Um, we will go back to in person on Wednesday. Bye.